Imagine your code suddenly stops, throwing a wall of cryptic text onto your screen. It feels like a detective novel without any clear clues, but what if that messy text actually held the exact map to your problem? That seemingly overwhelming output is often a stack trace, a powerful diagnostic tool every developer learns to love. Interpreting a stack trace entry fundamentally involves recognizing three key pieces of information: the method or function name, the class or file name, and the specific line number where an event occurred. Each line in a stack trace represents a single call in the execution path, providing a direct link to the source code. The reason stack traces are structured this way lies in the concept of the call stack itself. When a program runs, every time a function or method is called, a new frame is pushed onto a data structure called the call stack. This frame contains all the necessary information for that function call, such as its local variables and the return address. When an error or exception occurs, the system essentially takes a snapshot of this call stack, showing the entire sequence of active function calls leading up to the point of failure. It provides a reverse chronological order of execution, revealing the exact path your program took. To effectively use this information, start by locating the first line in the stack trace that references your own code, rather than system libraries, which are often listed first. This is typically the entry point where your logic initiated the problematic sequence. Once you identify that line, you can pinpoint the exact file and line number to examine. You can then trace downwards or backwards through the entries to understand the sequence of method calls that led to the error. This helps you understand the context of the failure, not just the symptom. Look for keywords like caused by or at, which clearly delineate each call frame. An often overlooked but crucial detail is understanding the thread context, especially in applications that handle multiple operations concurrently. A single stack trace usually applies to a specific thread, and in complex systems, multiple threads might be involved. Each frame on the stack is a unique snapshot of a single function call, containing a clear record of its local variables and where it needs to return. Knowing which thread encountered the problem helps narrow down potential race conditions or synchronization issues. Ultimately, learning to interpret a stack trace entry transforms a frustrating debugging experience into an efficient diagnostic process. By systematically dissecting each entry, you gain a deep understanding of your program's execution flow and precisely identify where and why errors arise, empowering you to resolve issues with confidence and speed.
If this helps you fix faster, like, subscribe, and keep debugging with us.